Merci Luc. Bonjour. Malheureusement, je ne parle qu'un petit peu français, donc I will continue in English. Okay. So I'm going to talk about Spark and how it augments Couchbase. You may notice that the title is slightly different from that on the agenda. Apologize for that. There were some last-minute alterations. But I think this is a really good overview from an architectural point of view, slightly higher up than down in the implementation details of why one would want to use Spark together with Couchbase, or Spark indeed at all. So the agenda, it looks like this. Why would we do this? Why do we want to integrate Spark with NoSQL, particularly Couchbase? And what architectural alignment is there between Spark and Couchbase? So Jean-François happily teed up some of the concepts that I will discuss, such as reactive event-driven architectures, doing things as they happen rather than just in batches, and also having every tier of your application and your architecture being able to scale totally. So we don't have any pinch point. We use things like Kafka in the example as the event bus to pass messages, and then you have scalable tiers like Elasticsearch and Couchbase below or above those in the architectures to make sure that everything can scale, so you build from the beginning to scale. I'm also going to cover some of the integration points. So how do we tie Couchbase into Spark? What interfaces do you have to do that? And why would you make use of the different interfaces? Including on the streaming side of things. So streaming, of course, extremely important. Hot topic, everyone wants to move towards stream-based architectures. And we'll talk about how the flexible schema of Couchbase is useful when you're integrating with Spark. And I have a little demo at the end, which hopefully will work if the demo gods are with me. So what we'll see is essentially a kind of next generation ETL process where we will stream data from Couchbase and we will join it onto data from a MySQL database running on my laptop using Spark, which illustrates some of the general principles that I will talk through during this presentation. So first of all, why Spark and NoSQL? It's worth coming at this from the perspective of the kind of use cases that are tied together with these technologies. So if we look at this slide that's on the screen behind me, on the left-hand side, we have the operational side of things. Couchbase fits in here, scalable architecture. And what we're trying to do here is to provide you deterministic, low latency response times to your operations, web-facing, web scale, out to mobile devices, for instance. And also let you do many hundreds of thousands of operations per second, tend to be kind of random reads and writes from Couchbase as the operational data store here. So on the other side of the slide, we have the analytics cluster in this illustration, and that's where we see Spark fitting in. So if I run through the content here, if we go down this list, if you have a catalog application, if you're a company like Walmart or Tesco, both of whom use Couchbase for this kind of use case, they want to store their product catalog. So you have ISBNs, you have IBANs, the identifiers for your items, you have a hierarchical data structure, Coca-Cola at the top, Coca-Cola 1 litre bottles, a 6-pack of 1 litre bottles, and so on. That hierarchical data structure maps very nice to Couchbase. And maybe we have, if we're someone like Walmart, many millions of items in this data set. So we want to service that information on the website so users can visit it, and we would service that from something like Couchbase. But what we also want to do is to be able to cross-sell and upsell. So pragmatically, we want to say, you are browsing this item, what item might you be interested in? And in order to do that, I need to potentially have used something like a machine learning algorithm, mlib in Spark, which is one of the powerful motivations to use Spark, that you are given this lovely library and package of distributed algorithms that I can run. And I can train a model which will say, if a user with this kind of activity profile looks at this product, then what would they like to look at next? What are they most likely to buy? And so the computation of that model would take place in Spark, and that involves me streaming the user's activities into that model to refine it and train it. But when I've generated my prediction, I need to service that prediction out to the customer. And the prediction is likely to have been written back into Couchbase here to be served out to the user. And a similar theme applies to a customer 360 or IoT data store. We want to aggregate information. So Nike use Couchbase. They take information from various different sources, retail channel, online channel, perhaps fitness tracking devices, so that they can say, I know this customer bought a pair of shoes, trainers, 6 months ago. They've run 200 miles. Maybe I want to offer them the next product. And so they might use that to have Spark kind of tie together the different data sources. Maybe the retail channel uses a sort of legacy relational database. Couchbase might be used for one of the other data sources. We want to tie that data together and aggregate it into a read model and store that back so that we can then power applications that have insight into the whole customer. And this sort of joining together that ETL process maybe would make use of Spark, and that's what we'll see a bit later on. Lastly, personalization. I'm a big fan of Spotify, streaming music service. By way of example, they will provide me weekly a playlist of music which is uncannily alike to my tastes. So a very accurate representation of what I might like to listen to. Now, they will have crunched a lot of data to do that. You know, they have hundreds of millions of users, and they have data from those hundreds of millions of users. And they need to do computation across that data set to identify trends and then to suggest me preferences. So the computation would take place in something like a Spark cluster, but then I need to be served my list of items. Well, that might map very nicely to a JSON, the track titles, the information, the summary, and I can very quickly load my weekly playlist just using a key value access to Couchbase. So two very complementary approaches to analyzing and storing data, Couchbase on the operational side, Spark on the analytical side. So this slide just weighs a bit more of what I was saying, dives into a bit more detail on the way we should reason about these technologies. Again, operational, analytical split, analytical, Spark, Hadoop, and operational, Couchbase in this case. Very much from the use cases, web-facing for Couchbase, analytics and machine learning for the analytical stores, of course. How do they process data? Couchbase in an online basis, lots of inbound events, perhaps being captured from your website, stored in Couchbase, and then passed off to be analyzed in your analytics cluster. Ad hoc querying with Couchbase, we have Nickel, the query language. I will discuss a bit more detail how that ties in with Spark SQL and how we can push predicates down and have Couchbase do the work there. So you'll see the two things tied together. But typically, it's an ad hoc process within Couchbase on the queries. With Spark, yes, you can do ad hoc, but you're more likely to know I need to push this data into some kind of analytics number crunching pipeline. And I define that in advance, and then I have that model running in my Spark cluster. So performance is an interesting point. We are aiming for predictability, and we are aiming for many hundreds of thousands, potentially, of operations per second, but with a highly deterministic latency, sub-millisecond response times, kindly delivered to us by my colleagues in the engineering team, some of whom are in the room. Whereas with something like Spark, yes, you want to operate on all of that event data that perhaps is streaming in. But your processes might actually take a long time. You know, what you want with Spark is high throughput. I want to make use of the memory I have available, but I want to be able to do a lot of crunching on large data sets. Now, that crunching might take minutes, it might take hours to do the processing, and indeed, you wouldn't use that tier to service up the results. That, as we discussed, would go back into Couchbase. So there are two distinct parts of this. A Spark job may run quickly, one may run longer, it may run hours, it may run overnight. Couchbase, very much, each operation we're looking for very low latency. But do notice that both Spark and Couchbase memory-centric architectures, making use of RAM. So we have complementary access patterns. We have similar types of speed in terms of data access. And that's where Couchbase can tie in very nicely with Spark. So the first use case, this is what this might look like. Probably we could think of this as the sort of Spotify example, or any streaming music service, Apple Music. They want to provide recommendations. So the user's activities are collected in Couchbase, and then we're streaming those activities into Spark, where we're creating our model using mlib, using machine learning algorithm. And we're iteratively refining that, possibly by streaming data, training data into Spark from Couchbase on a regular basis. The model is being updated. Predictions come back, they're written into Couchbase, and then we serve those predictions. On the left here, we have a small illustration suggesting a node layer. So the principle really that I'm trying to convey is we probably have some sort of thin API which lets us serve that stuff up. REST API provide access to the documents in Couchbase. Node, by way of example, of course, it might be Java Spring, it might be something in C, it might be something in .NET, any of the SDKs that we support. But the key point is this section in the middle. Training data flows into the Spark cluster from Couchbase, and the predictions flow back. So that's operationalizing, perhaps slightly American word there, but operationalizing your machine learning data, actually being able to do something constructive with it. So the second use case concerns integration, data integration. And you'll see from the example, the code sample that I have later, just how simple it is from a programming paradigm perspective to integrate various data sources with Spark. Now, I am not a developer, and I was able to comprehend this, put this together. So, what you want when you're trying to connect this stuff together is a nice abstraction layer that gives you a consistent interface that minimizes the systems you have to learn. And that is what Spark can do here. So you can integrate with any of the big data technologies that you would like to, very simply. And I can do this all in a clustered fashion and have the complexity of the distributed system abstracted away from me in a similar way that Couchbase does things. And particularly on Couchbase here, you'll notice 4 keywords there. DCP, which I'll talk about shortly, Database Change Protocol. That is Couchbase's internal streaming protocol, used by us for replication and for streaming data into services like our indexing service or into our MapReduce engine. KV, key value. This is the hash distributed data when I refer to consistent low latency deterministic performance. This tier is where we really achieve that. And this is pure get me this document or set me this document into the database. Nickel, N1QL, you've heard about that several times today. This provides an API which lets us do key value access, but it also lets us do things like range scans. So if you consider that the key value access is hash partitioned, then Nickel lets you access global indexes which can be range partitioned. So if I need to stream out data by username or by some field other than the primary key, Nickel can let me do that, and indeed write any ad hoc query that I like. Finally, the views here. This is the Couchbase MapReduce engine. I can use that to create aggregations across my data, incrementally updated. So if I know the question I want to ask, for instance, give me the total number of users who have logged in within the last day, so the date stamp is within a certain period, the user has a login flag on their profile document, I can have that aggregation incrementally computed, and when I want the result, I simply submit a query and I retrieve it straight from an index. So the computation is done up front and it's spread out across the nodes. So 4 interfaces in Couchbase. All of our SDKs give you an API that's very fluent, gives me a means to access these things. And increasingly the path is for us to kind of consolidate the access to these different portions of Couchbase into Nickel. I think that's the trend that you'll continue to see, is that we give you these different pieces behind the scenes, which give you the performance you need for certain tasks, and we'll continue to kind of abstract that implementation detail away. but it'll always be there if you need to eke out that last bit of performance, as indeed people like Amadeus and Criteo need to do. So the data integration architecture might look something like this. Here, similar to the picture before, Spark connects to my various data stores, HDFS, Hadoop file system, maybe S3, I want to stream out JSON files from S3, relational database systems, and potentially Elasticsearch, although we will talk about Couchbase's full-text search plans shortly. So if I do my crunching, dragging data between those systems using Spark to create an in-memory table of the data from the various things, I can then do joins across these tables in my Spark cluster, and I can write that data back to Couchbase. So in order to explain a bit more clearly how the architectures are aligned, I need to just touch a little bit on how Couchbase actually works, and a bit more on these interfaces that I mentioned previously. So there are 5 pieces on here, the last of which is full-text search. Bob and Ravi mentioned this earlier. It's in developer preview at the moment. It will be generally available in the next major release of Couchbase, and this will allow you to build inverted indexes and to do exactly as it says, full-text search across fields within your JSON documents or the documents themselves. For now, because it's developer preview, I will have it fade away, and we'll just concentrate on the generally available features. So firstly, the key value, directly fetch or set a particular record. Quite simple, hash partition data. The query engine. So by query here, I mean nickel. This lets me specify a set of criteria to retrieve a document. So the first method, I know the key. I know I want to get user profile Simon Leigh. The second one, show me all of the user profiles for users who live in London. I've created that index. I can send the query, select star from users where user location is London, for instance. So essential in reporting. My colleague Francois will talk a bit more about building reporting environments with Couchbase later on. MapReduce views, incremental process, good for aggregations, good for queries where I know I'm going to repeatedly ask this and I want to pre-compute the results. I can write on the server side a map function in JavaScript and a reduce function in JavaScript. And I can implement any logic I like in JavaScript. That's processed automatically every time data is written to the cluster. Those functions are triggered, and they insert data into an index based on the logic that you implement there. Data streaming is a particularly cool one, and a lot of our connectors, many of our internal services are built on top of this. The query service relies on indexes that are built by tapping a stream from the key value data service. Similarly, the MapReduce engine, again, takes a stream of the mutations that are written to the key value service and generates its indexes from there. So that's used by us internally, and indeed it's used by connectors like Spark, like Kafka, and to an extent the Elasticsearch connector, which uses our cross-data center replication protocol in order to stream data between systems. So a little on the key value portion. The way Couchbase distributes data is by hash partitioning. When you have your 6-node cluster, when you define a database, which we refer to as a bucket, we automatically divide that bucket into 1,024 vbuckets. And these vbuckets, virtual buckets, have a physical manifestation. So they live on a particular server. So if I have a 4-node cluster, I've changed it from 6 to 4 because I can more easily divide 1,024 by 4 than 6. I have 256 of the vbuckets on each of the servers. Randomized, nonetheless, each server will have 1/4 of the total. But because the order of those is not contiguous, the order is randomized, I need a map which tells me from a client where does the vbucket which owns my piece of data live. And this cluster map is created and maintained by the cluster. And every time a client connects, the cluster says, here is the layout of the data within the cluster. So every client connects directly to the location of the data. It also knows where the replicas are, so if a node fails, I can read directly from a replica. The cluster map is really the differentiator in terms of us being able to provide consistent access to the data, but also allows us, because we're hash partitioned, to give you sort of order 1 access to data in terms of time, regardless of the amount of data in the system, because we just need to identify, I hash my key, on which server does it live, directly connect. I don't have to traverse an index to do that. That's why our response times are deterministic. The time to hash a key is the same regardless of the key. So the mapping is extremely important, and the mapping we can in fact take advantage of with Spark in terms of ensuring data locality, which I'll touch on shortly. For Nickel, N1QL, this is the SQL language which lets me query JSON, which lets me generate indexes on that JSON. It's stateless execution, but it uses Couchbase global secondary indexes. So I can say create index on this bucket, on this field, the index is created, and then if I write a query which can use that index, it will be traversed and the results will be streamed back to me in JSON. So there's the query engine, which will pass, tokenize, plan your query execution, and there's the indexing engine. They might be co-located, or they might be distributed physically. So if they're completely distributed, so I have an indexing node, a query node, and I have data nodes, multiple of each for high availability, we would call that multi-dimensional scaling, which was on the t-shirt I was wearing earlier, but indeed is on, I think, the next slide. So if we multi-dimensionally scale, we can have the services running independently. We can dedicate hardware and maximize workload isolation. The views, JavaScript-based, generates a B+ tree, does the work in advance, so does the work when the document's written. So when I query, the computation's already done. Nickel, ad hoc querying, the computation may or probably will be done at the time that I query. These are always, so the MapReduce engines run per node. So they're co-located always with the data service. So if I have my 4 data nodes, each one will run this engine, and it will process just the data that belongs to it. So with the MapReduce paradigm, we're stretching out where the computation is done. It means that when we do issue a query, we have to ask each of those servers to respond, and then we do a merge sort at query time. Finally, the streaming. This lets us do things like stream all of the data out that's ever been written, and then keep streaming to me. And indeed, that's what I will do when I turn on my Spark demo later. Or I can say, start from now, because the protocol allows for snapshotting. I can say, what's the latest snapshot? Stream me data from there. Or if I want to totally migrate the data out and transfer to another system, transfer to another cluster, I can stream everything out, transfer it to another Couchbase cluster over cross-data center replication, and then turn off my old cluster. So how do these things map to the concepts in Spark, and what do they let us do within Spark? Well, the familiar picture that we've just seen, this is how things link together. Using a key value access, I can produce an RDD and store it in my Spark driver. So I will touch a little bit on an RDD. An RDD in Spark is a resilient distributed data set. You could envisage it as a table of data, so set aside the streaming piece for now. You could envisage it as a table of data on which I can apply transformations or I can apply actions. So a transformation may simply be I want to filter out certain pieces from that table based on a predicate and create another data set. Or I might want to take some action on it which will sum up the number of rows and then give me an output. An RDD is the kind of principal paradigm object that is moved through Spark. It's resilient because they can always be rebuilt by keeping sort of a history of how that piece of data came to live and then recreating it if a node fails. So Spark is highly available, very resilient, just as is Couchbase. Querying, I can use Spark SQL to create these RDDs or data frames or data sets in more recent versions. And the cool thing with Spark SQL is that it can push down predicates into Couchbase. Or Couchbase is able to say, if I express a filter within Spark SQL, that filter can be pushed down, Couchbase can do the filter, and then return only the rows in a Spark context, only the items from a JSON document within Couchbase that I'm actually asking for. And in a distributed system, it is shuffling data around, that is the killer of performance, as was kind of, in earlier versions of Hadoop when we were doing Hadoop MapReduce, writing everything to disk, and then having to take that state, load it up into RAM on another machine, do the processing, and write to disk. That is what slowed things down. It's now mainly obviated by advances there, but it's kind of a problem that Spark is solving by doing things in memory. So if we use the MapReduce views, we can query that view, we can create an RDD from the result of the view, and streaming, we can connect into Spark DStream interface, and then we can apply transformations as the documents come out of Couchbase. So in version 2.0 of our connector, which is due towards the end of this month, we will support Spark structured streaming as well, so you'll be able to put some more typing on the data structure that comes out. So automatic sharding, the point I made about the data being distributed throughout the cluster. If you have one Spark worker node running on the same, on one Couchbase node, then we can push down location hints. So if you wanted to temporarily store data within Couchbase, we can use the cluster map to say, I want this piece of data available to this Spark node. I know that there's, from the Couchbase cluster map, I can store data in this partition, in this vBucket. And so it can push that hint down and it can write it locally. So that means we minimize the distance between the data moving around, keeping the data near the computation. That's available because we can use the cluster map for the data service. However, for Nickel and Views, because as I said, those services are kind of dedicated on individual machines or they're living together, but they're not hash partitioned, then we round robin between those services, rather than being able to give location hints. And with Views, the back end is scatter gather. We're doing that merge sort at the end. So a little bit of detail in the difference between those two interfaces, how they work within Couchbase. So the predicate pushdown that I've been referring to. Within Spark, if you want to tie into Spark, it is possible to implement one or three of these interfaces. So the first is the table scan, and this essentially says, from Spark, I just want to get from this table or from this bucket in Couchbase everything, all rows, all columns. In our sense, all documents and every single value within those documents. So this is the kind of most naive, just suck the data out, put way more than I need in memory within Spark, and then start doing transformations there. A prune scan, which is the next level, lets me say, from a Couchbase perspective, let me connect, get me every document, but only give me a subset of the content. So this, from a kind of rows and columns perspective, would be drop these columns before you pass all the rows back to me. So still all of the data, but doing some slicing on columns we're not interested in. The prune filtered scan is the one that we have implemented, and this lets me say, I only want these rows, and I only want these columns. So it's the most efficient way. It minimizes the data interchange between the data source and Spark. So we pass through our query optimizer, making sure that your predicate's pushed down, and making sure that we only pull back into Spark the data that we need, rather than having to pull everything and then reprocess those predicates. So from a topology point of view, if you make direct document updates to Couchbase, they go directly to the data nodes. The data might stream then from the data nodes into an index, the global indexing service. The query service is not involved here. I'm just saying set this document, get this document. And in this case, the application client might well be a Spark worker. If we do want to query using a ranged query, then we go to the query service, which will consult these secondary indexes. And because these are B trees, we have logarithmic time in terms of retrieving data from the indexes. So there's a trade-off there. We have more flexibility. We can do the range scans, but we're trading off the time complexity. And for anyone who's interested, this is a brief example of us using the Scala or Spark pattern matching in order to push down attributes. So if something is equal to, then within nickel, it uses the equal sign. If it begins with, ends with, we're using a like. And Spark will automatically build up using its pattern matching features from Scala the right predicates and push those down to the Couchbase nickel engine when I ask a question. So some of the notes from our engineering team on implementing this, Spark assumes still, or at least in version 1.6, that it is going to get all of the data from the data source. So it will try and reapply any predicates that you specified. So even though we're doing that pruned filtered scan, we're pushing back only what it asked for. It will try and do the filtering again. So there's a computational step that it tries to do, and that's just part of Spark. Really, it doesn't cost you that much because it won't find any work that it actually needs to do. It just tries to do it. There are more things that we can do. So this push down all the things, this whimsical character wants all the things, and we want to do, push down aggregations to Couchbase using the MapReduce views, push down joins to Couchbase using our join syntax in our query engine. We're also looking at ways that we can optimize things, extend the Catalyst engine that powers Spark SQL. So if you want to use streaming with Couchbase and Spark, points to note, it's very common, and indeed Jean-Francois was talking about essentially reacting to events sourced on Kafka, pipelining those into other systems and doing computation on them there. So this is indeed where the streaming ties in from Couchbase. I talked about the Lambda architecture last year at this conference. CQRS, again, maybe we, as data comes in, the way that we write it, the way that we store the data, then is in one format, in one view, but we want to do some processing at that point so that when we want to read it back out, we have a different model. So we might be doing a transformation as soon as the data streams in so that we create our read model. And we can use Spark to do that, and we can stream the data from Couchbase in order to power it. Or many other reactive patterns as well that fit into using streaming. So typically, documents flow. The picture from the previous presentation was better. Documents are flowing from somewhere, possibly from a message bus, event bus. They come into the system from outside. They enter Couchbase. They're persisted. And then they stream off to your Spark cluster, or they stream off to Elasticsearch, or the replicas are streamed off to other Couchbase nodes. And most commonly, this happens from memory to memory. So that covers the kind of integration points around Spark and why it suits Couchbase. What I'd like to do now is to try and actually show what that looks like. So for those who haven't used it, to try and illustrate what it looks like to actually join data from two data stores doing a transformation job with Spark. So hopefully this will work, and the screens will show the right thing. Okay. So what we're going to see, if I show you the source data, that's visible. So I have a MySQL table. And in that table, I have data in the form of 4 columns, people's given name, their surname, their email address, and some sort of entitlement token. So we could consider that this data set, these entitlement tokens, live only in MySQL, and we need to push those out to our web-facing tier. So Couchbase is powering our website, and we have the same identities. In this case, the email is the unique key. And we want to surface the entitlement tokens here up to our user profiles within Couchbase. And we want to make sure that whenever a user makes a new profile within the website within Couchbase, we immediately go and check in MySQL, do we have that data? Can we enrich that profile immediately? So as they create their profile, we stream the data out, we do the enrichment, we write it back. So as soon as they have created their account, we've done the enrichment from data we already had on them. So this is the kind of trivial MySQL table. And if I log into Couchbase running on my machine, you'll see that we have, this is showing the documents within this transformative bucket. The bucket, the database abstraction that I spoke of earlier. We have user documents, user profile documents. And if I look at the first person here, these match to the data in MySQL, but they're missing my entitlement tokens. So of course, typically we'd have many more fields that are used in our web application. But what, in principle, we want to do is, for all of the existing users, enrich their data, and for any new users who come along and create their profile in Couchbase, do that enrichment. And we can do that using Spark. So I have an example here. I just want to concentrate not on the kind of reasonably simple functions that do the data combination, but on how easy it is to actually connect to and gather data from these sources. So in the main function here, so this is essentially the driver that is going to be deployed to my Spark cluster to do my connection to my SQL and to connect to Couchbase, stream things from Couchbase, join them to MySQL, and write them back to Couchbase. So if I first enable DCP on the Couchbase connector, create a new instance of a JDBC driver to connect to MySQL, then I can just get a MySQL reader. So I'm using the classes that are provided to interface with these systems. And in order to load the entitlements, so those entitlement tokens, I'm just calling load on the MySQL reader. The configuration for that's defined slightly higher up. All it says is, please connect to the user database and the profiles table. So that's me loading the entitlements into Spark. So it's going to load that table of data from MySQL into memory, and I'm then able to do a transformation on it. So if I take an RDD, so the data set that I was describing earlier, and I can create this by pulling out the email from the columns in the MySQL table and pulling out the entitlement token. So now I essentially have a tuple where I can match email as the first element and entitlement token as the second element. So I've got my data from MySQL in the way I need it. I can also, let me try and bump the font up slightly here quickly. I feel it's slightly small. I can also then create a Spark streaming context. And once I do that, I can create a Couchbase stream on it. And this is from my transformative bucket. So now I'm connecting a stream to all of the mutations that come into my Couchbase bucket, and I will get the mutation as it occurs. And I want to filter it. So from that stream, I'm going to filter those elements that are a mutation, as opposed to something like a delete, for instance. And I will take from any mutations the key of the document, and I will take the content of the document, again, creating a tuple here in the map. And from that, I'm generating RDDs. So I filter them again. I say, any of these documents that don't already have an entitlement token need to be enriched. And you can see I'm just chaining my transformations here. I could do this and assign variables at every stage, but I'm just chaining the whole process. I'm then filtering out from the second element of the tuples, the content of the documents. If I find that there's an entitlement token, or I find that those where the entitlement token is null, as in the field doesn't exist, I know I need to do the enrichment. And so the enrichment is take the document, join it onto my table of entitlement sans schema, which is the email address and the entitlement token we pulled from MySQL, merge that entitlement token into the document, and then finally at the end of my method chain I just say, with this RDD, save it back to the Couchbase bucket. So that's going to stream the documents out, see if they need enrichment, enrich them from the MySQL data source that I've loaded, and then write back the enriched document. I will start this process. And just to remind you, at the moment, these documents don't have the entitlement on. If I run this example, Spark will fire up, deploy one worker on this machine. And it's now streaming the documents from Couchbase. So if I go back to this documents bucket, it's streaming out all the mutations as they were written into Couchbase. And you might notice the second one here now has an entitlement token. So it's going back from the beginning of each vBucket and streaming them out. And it's worth noting that the first entry here, so Leigh Armstrong, was enriched after the second. And that's purely because when I loaded this data, the first items that were written were from somewhere lower down the alphabet. The ordering of the keys for that iterative process was not the same as the natural order here. So I'll actually show how, when I do mutate things in order, you'll see that the updates will go through in order and the first entry will be mutated. But you can see that Spark is running away. It's still processing down the bottom. If I have a look at the Spark streaming statistics, we can see that it's running 550 events per second. It's only on my laptop, so of course we're resource constrained here. But the stream, once it finishes processing all those historical writes into Couchbase, so it catches up. And I should mention, I'm not actually doing any work in Couchbase at the moment. I'm not mutating these things. It's now finished, and it has enriched all of the documents in the bucket. So if I were to go through all of these documents, they've all been joined to the data that was in MySQL. So we've connected two data sources and done a transformation job. So if I now use, to prove that the stream is still running and that any further mutations will be processed, what I can do is use Couchbase's query language to essentially fight with Spark. So this query will update all of the documents in the transformative bucket, and it's going to remove the entitlement tokens. So when Spark sees that mutation come in, it will hit the predicate that says, is the entitlement token null? Yes. And it'll go and do the join again. So this is to simulate new entries being written. So I have 10,000 documents. If I execute this query, then we will see that 2.5 seconds, all of the entitlement tokens are removed. Spark is whizzing away again here, attempting to fix my unsetting of the entitlements. And you can see that the entitlements have been written back already. If I go further down the data set, and it may already have beaten me here, but if I go and look at documents that begin with the letter T, for instance, I think it's written too fast. Okay, so it hasn't actually enriched these yet. And that's because when I made that change using Couchbase's Nickel engine, the order of the keys that got mutated was actually the natural lexicographic order of A, B, C, D. So it's running through the mutations essentially in order as they happen when Nickel changed things. And you've just seen it reached T and it updated those documents that were mutated later. So the principle we're seeing here is playing back mutations so that I can enrich an existing data set, but the stream continues. Spark is still connected to Couchbase. And when I make changes in Couchbase, it then goes and continues the enrichment process. So we're having the initial batch processing, and then we're using the streaming to continue to enrich data as it's written into Couchbase. This is all on my one machine. Spark will do the optimizations for you. We'll compute the directed acyclic graph to try and distribute the work if you have a cluster of nodes, and you won't need to change your code from that which I saw here, which I showed you here. It will automatically deploy workers and drivers and distribute this for you if you have multiple machines. Similarly, Couchbase, as my data set increases and as I write more data, I create more indexes, Couchbase will distribute that data for you and will also allow you to build indexes, distribute them seamlessly through the cluster, make sure they're highly available and that you have copies of them, and do this all very simply through our API, or if you like, just through Spark's API, which then lets you be abstracted one level above your data stores and lets you use the language of Spark's analytics and Scala to interact across multiple data services and do the work you need to do without getting bound up in the weeds of the implementation detail. So that's it from the demo perspective. I hope that was instructive. I'm happy to take a couple of questions in a moment. I just want to cover the features that are due to come in the next version of the connector. So we will fully support Spark 2.0. Currently, we support 1.6. This connector is due this month. We're rewriting the DCP integration. So the library is being revamped, and it will let you have more granular control over when you start streaming, when you end streaming, and snapshotting to fully comply, essentially, with Spark structured streaming, which I recommend reading about. It's very interesting. Essentially gives you an abstraction of an append-only typed data set or a data frame, if you're familiar with R or Python, pandas, things like that. So that's what's coming next. Our colleagues are busy working on it at the moment, and it should be released this month. That is it from my kind of introductory Spark and Couchbase talk. Thank you very much, and I'll take any questions if you have them. Okay. Thank you. So thank you very much. So the one question, if you come and grab me, then afterwards. Okay, perfect. Yeah, let's go.
Oh, thanks for the presentation. Is it working? Yeah. Okay. Cheers. So yeah, I had one question regarding the way you handle streaming, because in the previous architecture that was demonstrated by Ingenico, they were having Kafka upstream.
Yes.
And this, in your case, you're relying on DCP. So what are the advantages, or what kind of difference you see in choosing one of the architecture or the other? Yeah,
that's an excellent question, which is, why would you stream directly with essentially DCP into Spark from Couchbase versus streaming from Kafka and possibly pushing that into Spark or Couchbase and so on? And the answer is, it depends on the level of abstraction that you want. So Kafka is something else to maintain. So similar principles as everything else. Kafka is great. We have many customers who use it, both to push data into Couchbase, so they will subscribe to a Kafka topic and receive those messages and write them to Couchbase. You can also use the Couchbase Kafka connector to publish messages into your Kafka broker and Kafka topics. So I think that if you have Kafka, then great, you probably want to use that as your sort of event sourcing system, the event bus that you plug everything into, and you have control over what's going into that and how you're digesting it. And maybe then you will just connect Kafka into Spark, essentially, and do your processing there. If you don't have Kafka, then you might still want to enrich the data from Couchbase. So it's a question of what works for you in your architecture. If you want the abstraction of Kafka, if you want to use it for other things, awesome. I see it both being data sourced from Couchbase being pushed into it, and both writing data from Kafka into Couchbase. I think it really depends on whether you want another system to maintain and whether you get more flexibility or just something else that you have to deploy and run. So I don't think we necessarily have a preference. The Kafka connector, actually, the next version will use exactly the same DCP library as the Spark connector. So they'll have the same functionality in terms of how they can stream the data. So it's entirely up to you. It's about giving you choice rather than dictating what's better. Okay, one more question here.
Hi. My question is about the Couchbase part. So there is a stream coming from the customer and a stream going to the customer. I wonder what would you recommend as architecture? Do you recommend a separate Couchbase cluster for incoming and outcoming, or the same cluster for both the stream?
Okay, good question. So good that you're making me use the slide that I prepared, but it's not correctly formatted. So I'm very sorry, Luke. Oh, it looks okay. So the right-hand side shows 2 Couchbase clusters. So I should repeat the question. Do we think that in terms of the inbound stream, have one Couchbase cluster to store that, and then have another that pushes the data out, or that receives the outbound stream of mutations? And it depends on whether you need workload isolation, whether your cluster can handle doing both things. So it is true to say, and I would probably get ticked off by the engineering team, that there's no such thing as a free déjeuner. So you don't get a free lunch, and if you attach lots of stream consumers to Couchbase, then we're having to push that data to those systems, and it puts extra load on the cluster. So if you have very many inbound writes, and your cluster is heavily loaded, and I mean, you know, it's likely to be hundreds of thousands of mutations a second to really push a sizable cluster, you may not want that cluster to be doing other things, computing views or indexes and pushing data elsewhere. So for smaller deployments, many of my customers do everything with 3 nodes. They have a number of CPUs on each node, and they just use one cluster for writes, reads, everything. And that works up to a point, and it's fine. If you feel you need to scale beyond that, as kind of is illustrated here, then you might want to isolate the clusters, use our cross-data center replication between them, and then you're isolating your workloads. So what I would say is if you know in advance you're going to have very high workloads and that you can test this stuff, so David is going to talk later about planning for scale, planning for lots of load. If you simulate this and you find that you need to have a split cluster, then start with that topology. But if you're starting small, then there is very little work involved with Couchbase to expand things and to actually separate it. You'll find that it'd be quite easy to split the clusters out, change a couple of lines of configuration in your application to route the different requests to either cluster. So starting small is fine, sharing the workloads. As you scale, you might find you want to break it out, but because it's so easy and totally online to do these kind of migrations, you might find at a later stage it's split. So entirely up to you. Okay. Thank you very much, everyone.